We're about to dive into something that's pretty fundamental to our digital world. How do computers actually see? We're going to break down the whole process, starting from a single dot of light and building all the way up to a machine that can recognize the shape of an object.
Okay, let's just jump right in. On the left, you've got a normal photo of a car, and on the right, well, it looks like a simple line drawing of that same car. But here's the thing, an artist didn't make that, a computer did. So the big questions are, how in the world does a computer do that, and why is that simple drawing so incredibly important for AI?
To get to the bottom of that, we're going to walk through 5 key ideas that are basically the building blocks of computer vision. First up, we'll see how pictures are really just numbers. Then, we'll talk about color. After that, we'll figure out how a computer finds edges. Then, we'll meet a cool little tool called the convolution kernel. And finally, we'll see why these edges matter so much.
So, let's start at the very beginning with the most basic idea of them all. Before a computer can even think about seeing a car, it first has to understand what an image is in its own language.
Every single digital picture you've ever seen is really just made up of millions of tiny little squares. We call these pixels. The best way to think about them is like tiny individual tiles that come together to form one giant mosaic.
Now, for a computer to process any of this, each one of those little pixel tiles gets a number. This number represents how bright it is, its intensity. It's usually a value from 0, which means pure black, all the way up to 255, which is pure white. And yeah, you guessed it, every shade of gray is just a number somewhere in between.
And this right here is the absolute key. When a computer looks at a photo, it doesn't see a person or a place, it just sees a giant grid of numbers. That's it. It's all just a big matrix of data. And understanding this is what makes every filter, every edit, and all of computer vision possible.
Okay, so that was for black and white images. But what about color? Well, that's where things get just a little more interesting. With color photos, each pixel isn't described by just one number, but 3. One for red, one for green, and one for blue. You can literally think of a color image as 3 of those number grids we just talked about, a red one, a green one, and a blue one, all stacked right on top of each other. Now, keeping track of 3 different number grids for every single image, that's a lot of data for a computer to crunch. And honestly, for a lot of tasks, like just finding the basic shape of something, you don't even need all that color info. That's why, a lot of the time, the very first thing a computer does is convert an image to grayscale. It squishes those 3 layers down into one, making everything much, much simpler to analyze.
And this whole idea of simplification is huge, because it's the key to our next step, teaching the computer how to find the most important parts of an image.
So what even is an edge to a computer? For you and me, it's the outline of an object, right? For a computer, it's all about the numbers. An edge is simply a place in that big grid of numbers where there's a big, sudden jump in value, like when a really dark pixel is sitting right next to a really bright one. Take a look at this super simple plus sign. I mean, to our eyes, the shape is just there. It's obvious. We immediately see the lines between the gray shape and the white background. And this perfectly shows us what the computer sees. On the right, that's the number grid for the plus sign. You can literally trace the shape in the numbers. The edges are those cliffs, right where the big background numbers, like 255, suddenly drop down to the smaller numbers of the plus sign itself, like 67. So how does a computer automatically find all these numerical cliffs across an entire complicated image? It doesn't guess. It uses a really clever little mathematical detective to do the work. And that detective is called a kernel, or sometimes a filter. It's just a tiny little grid of numbers, usually 3 by 3, that's designed to spot a specific pattern. Think of it like a tiny magnifying glass that we slide over the whole image, and it's built to light up whenever it finds that specific pattern it's looking for, in this case, an edge.
This whole process of sliding the kernel over the image is called convolution, and it's really a pretty straightforward 3-step deal. You take your image grid, you apply the kernel, and you get a new grid as your output, which we call a feature map.
So here's how it actually works. You take the kernel and you place it right over the top left corner of the image. Then the computer multiplies each number in the kernel with the image pixel right underneath it. It adds all those results up, and boom, that one final number becomes the very first pixel in our new output map. Then you just slide the kernel one spot to the right, and you do the whole thing again. Multiply, add them up, and you get the second pixel for our output map. And this just keeps on going. Slide, calculate, all the way across the first row of the image.
Once it hits the end of a row, it just moves down one and starts again, scanning the whole image piece by piece. What you end up with is this brand new grid, the feature map. And here's the magic. This new map is going to be brightest in the exact spots where the kernel found the pattern it was looking for.
All right, so we've got the mechanics down. Now we can finally connect all of this back to that car we saw at the very beginning.
So let's go back to the car. That line drawing on the right, that's not a sketch at all. That's the feature map that the computer created by running an edge detection kernel over the original photo. It has gone through pixel by pixel and highlighted all of those sharp changes in brightness, and in doing so, it has effectively drawn the outline of the car.
So who cares? Why is this so important? Well, it's because the edges contain almost all the critical information you need to identify an object. You can recognize a car from just its outline, and it turns out so can a computer. This process lets the computer cut through all the noise, the shiny paint, the reflections, the background, and focus only on the fundamental shape that screams car.
So we've seen how some pretty simple math can turn a chaotic sea of pixels into a clean, meaningful outline. It's an absolutely foundational step that makes so much of modern AI possible. Which, of course, leaves us with a final question to chew on. If we can use math to teach a computer to see the lines that define an object, what's it going to take to teach it to truly understand our world?